Okay, think about this. For like 50 years, the way computers handle information has been built on this one core idea, a rule everyone just accepted. But what if that rule, the very foundation, was actually holding us back? And what if someone just came along and didn't just bend the rule, but completely shattered it, opening up things we thought were just sci-fi? Today, we're doing a deep dive into something pretty bold. It's a provisional patent application for a cognitive prosthetic system. And look, this isn't just a faster chip or a minor tweak. It claims to completely redefine, right down to the basics, how information is structured, how it's accessed. It's about fundamentally changing the link between the ideas we have and where those ideas physically, live inside a computer.
That's a great way to frame it because, yeah, for decades, computer science has basically worked on this assumption. You have to separate the logical structure, your folders, your categories from the physical storage, where the bits and bytes actually sit on a drive or in memory. There's like a wall between them. And this deep dive, we're exploring how this new system doesn't just question that wall, it seems to, tear it down. And the results, the outcomes they're claiming, are really quite astonishing, could genuinely reshape things.
Right. So our mission today is to unpack how this invention is supposed to, 1, amplify our intent, make computers understand us better, 2, boost performance in ways that honestly sound kind of nuts, and 3, even introduce quantifiable AI safety, like moving trust from just a feeling to something you can actually measure, all while getting these performance numbers that seem, almost impossible.
Yeah.
So let's get into it.
Yeah.
Okay, to really get what this patent's driving at, we need to understand the problem it's tackling. This 50-year problem, the wall between logic and memory. It goes way back since, 1970? E.F. Codd's relational model. That basically set the blueprint for databases. And the rule was logical data organization, totally separate from physical memory layout.
Yeah.
That's just how you do it. End of story.
Exactly. It was the dogma. And it seemed logical, right? Keep things neat, separate concerns. But that separation, it's unintentionally baked in some serious limitations, really persistent ones. The first one, let's call it translation overhead. Think about asking a simple question like, find all cardiac patients over 65. Seems easy for us. But for a traditional system, oh man, it's this whole chain reaction. First, it has to parse what you mean, your intent, then translate that into, say, SQL. Then the database has to figure out the best way to run that SQL query that's optimization. Then it needs to look up indexes. Basically a map telling it where the data might be stored physically, like a library's card catalog.
The card catalog analogy.
Yeah, and only then does it go fetch the actual data from the disk or RAM. And finally, it has to assemble all those bits and pieces back into an answer you can understand.
Wow. Okay, so each step
takes time, adds latency, burns computation, and crucially, you actually lose a bit of the original nuance, the original intent at each translation layer.
Okay, that makes sense. What's the second limitation?
Second is correlation accumulation. Databases start out nice and tidy, right? Different types of info in different boxes. That's called normalization. But over time, in the real world, these categories that were supposed to be independent, they start getting tangled up.
How so?
Well, data gets updated, linked in new ways. Think of, customer purchase history suddenly becoming strongly linked to product support requests in ways you didn't initially plan for. These correlations creep in, and once the correlation between supposedly separate categories gets too high, the patent mentions around 0.5 performance just tanks.
Exponentially, you say?
Exponentially. It's like trying to sort a library where half the history books are mixed in with the science fiction. It just grinds to a halt.
Yikes. Okay, and the third one?
Opacity. This is a big one, especially with AI. Because of that separation between logic and physics, AI systems become black boxes. If an AI makes a weird decision, trying to figure out why means trying to unpick all those translation layers, all those optimizations, all those lookups.
It's like trying to understand how a cake was baked just by looking at the finished product.
Exactly. You can't see the ingredients, the steps, the oven temperature. You just have the result. And that opacity, it kills trust. How can you rely on a system if you can't understand its reasoning, especially for important stuff?
Okay, so these issues, translation overhead, correlation creep, opacity, they're not exactly secrets, right? People must have tried to fix this before. I mean, you hear constantly about things like vector databases now, Pinecone, Milvis, Weediates. Aren't they solving this?
An excellent point. And yes, many brilliant people have tried. Vector databases, graph databases, even things like content-adjustable memories or CAMs.
CAMs?
Yeah, specialized hardware where you search by content, not address. And neural networks themselves, in a way. But none of them have fundamentally broken down that wall between logic and physical location. They work around it.
Okay, so how do vector databases fit in then? They seem relevant.
They are, and they're clever. They achieve what's called meaningful proximity. Similar concepts get clustered together in this high-dimensional mathematical space.
Like grouping similar books on a shelf.
Precisely. All fantasy novels together, maybe. But here's the catch. The address of that cluster, its location in the computer's memory, it's still just an arbitrary pointer. It might be index number 4729, or coordinates like, point 2, point 7, point 3. That address itself tells you nothing about the meaning.
So you still need to.
You still need to do a search. A computationally expensive similarity search, comparing that vector to others using fancy math like cosine distance to figure out what that location represents. The card catalog, that index lookup step, it's still there. It just looks different.
Okay, that's a critical distinction. The address isn't the meaning itself.
Exactly.
And this is where it gets really wild, because the giants of the field, the authorities, they explicitly warned against doing what this patent claims to do, like C.J. Date back in 2003 saying it leads to brittleness. Stonebreaker in 2018 saying these attempts consistently failed. Gray and Reuter in 93 calling the separation necessary. It's like they put up giant do not enter signs around this very idea. So why on earth would someone ignore all that and try it anyway?
Well, that is the million-dollar question, isn't it? And the answer, according to this patent, lies in a really unique combination. Active orthogonality maintenance, coupled with direct position meaning correspondence. Together, these create what the inventors are calling computational pocket dimensions. It sounds dramatic, but let's break it down.
Okay, computational pocket dimensions. Let's start with the position meaning part. You mentioned the unity principle.
Right. This is the core paradigm shift. We're moving away from just meaningful proximity where related things are near each other. We're moving to meaningful identity. The address is the meaning. The map is the territory.
The map IS the territory. Okay, give me a concrete example.
Think of a piece of data like a patient's heart rate within their cardiac health record. Logically, you might think of that path as health.cardiac.heart rate.
Makes sense.
In this system, that semantic path doesn't just point to a memory location. It directly translates deterministically into a physical address. Maybe something like 0x17B00C0.
Without any lookup table.
No lookup, no index, no card catalog. The name is the location. The structure is the storage.
Whoa.
The patent argues that semantic structure, physical memory layout, even hardware access patterns, they aren't three separate things. They're just different ways of looking at one single phenomenon.
Like electricity and magnetism being aspects of electromagnetism.
That's a fantastic analogy, exactly like that. It's aiming for a unified field theory, but for computation.
Okay, that's a huge concept. But you said it's combined with something else, orthogonality.
Yes, orthogonality maintenance. Remember how we talked about traditional databases getting bogged down by correlations, categories bleeding into each other?
Using a performance killer.
This system actively fights that. It works constantly to keep different semantic categories independent or orthogonal. Think of patient age and diagnosis type. This system ensures they remain mathematically separate, so accessing one doesn't interfere with or depend on the other. It monitors and adjusts to maintain this independence.
How does it do that?
The patent describes continuous monitoring and adjustment mechanisms referenced in Fig Go 2. But the why is what's crucial here. When dimensions or categories are truly orthogonal, truly independent, performance gains become multiplicative, not just additive.
Multiplicative, meaning?
Meaning if you have three independent factors improving performance, the total improvement isn't P plus P euro plus P, it's PLI times P times P.
Okay, so small gains in multiple areas compound massively.
Massively. Imagine 10 factors, each giving a 1.5x boost. Additively, that's a decent improvement. Multiplicatively, that's 1.5 to the power of 10, which is over 57 times faster. It completely changes the scaling game.
Okay, that explains the performance claims, which are frankly staggering.
Right.
Let's look at the numbers they published, referencing EVE 04 and EVE 09, medical diagnosis. On a big data set, 10 million records, 361 times faster than a standard B-tree database, and 184 times faster than a vector database.
And look at the actual time, 0.125 milliseconds average query time. Compare that to 45 meters or 23 meters. It's a different league.
Then financial risk assessment. NYSE data. 8706x faster than a hash table, 135x faster than one of those cams you mentioned. Average access time, 0.089 microseconds.
Microseconds, that's incredibly fast.
They also showed huge gains for brain-computer interfaces, 40x less latency, and supply chain optimization, 3,750 times faster.
The consistency across different domains is also quite striking.
But the one that just floors me is the energy efficiency.
Ah, yes, that one's
1
mind-blowing.
million operations per second using 0.0072 watts.
Right.
Compare that to a top-tier NVIDIA GPU needing 400 watts for the same throughput. That's carry the one.
Huh.
55,294 times more energy efficient.
It's almost unbelievable. It suggests a fundamentally different way of performing computation at the physical level.
It really does. It makes you pause and think, doesn't it? If this is real, what other assumptions have we been making that might be wrong? For people hearing this, maybe skeptics, what's the likely pushback? What's the yeah, but?
Well, the biggest hurdle is always challenging dogma. When something claims to overturn 50 years of practice and shows numbers this dramatic, skepticism is natural, even healthy. People will question the benchmarks, the specific implementations, the generalizability. But the patent argues these aren't just speed-ups. They're emergent properties that naturally arise from combining that unity principle with orthogonality maintenance. You can see this in FI7 and FI8.
Emergent properties, like what?
Okay, first, exponential amplification. We touched on this. More dimensions, more orthogonal categories. Don't slow it down, they make it faster. Performance improves exponentially with complexity, which is, well, it's the opposite of how things usually work.
Completely counterintuitive.
Totally. Second, something they call computational morality. This is fascinating. The architecture itself makes beneficial operations, things aligned with the system's intended structure, computationally cheap, like O log n complexity, super efficient. But harmful operations, things that disrupt the structure or misuse information, become incredibly expensive, scaling maybe at ON.
So it's inherently harder to misuse the system than to use it correctly.
That's the idea. They mention 100,000x cost difference at a certain scale and 1,000. It creates an economic forcing function. It's simply cheaper and easier to do good than bad within this architecture.
Wow. Okay, what else?
Third, anti-fragility. It's not just robust, meaning it resists breaking. It's anti-fragile. It actually gets stronger when stressed.
How's that work?
Perturbations, errors, unexpected inputs, these trigger the system's orthogonalization process. It reorganizes, reinforces its structure, and actually improves performance in response to the stress. It learns from chaos.
Okay, that's wild. Stronger under pressure.
Fourth, inherent explainability.
Yeah.
Because the address is the meaning. Every single operation, every decision leaves a clear, traceable path through this semantic physical space.
No more black boxes.
Exactly. Complete audit trails built in. You can always see the why behind a result.
In the last one, trust something.
Trust debt measurement. This could be huge. The idea is that anytime the system's behavior starts to diverge even slightly from its intended semantic structure, it creates tiny, measurable glitches at the hardware level.
Hardware level, like what?
Things engineers track already, but here they gain new meaning. L2 cache misses the CPU, needing to look further for data. Pipeline stalls the processing flow, getting interrupted. Branch mispredictions, the CPU guessing wrong about the next step. You see this referenced in EV3.
So normally those just slow things down a bit.
Here, they become quantifiable signals, a measure of how much the system's operation is drifting from its defined truth or intent. They call it trust debt.
You can measure trustworthiness
Yeah.
objectively.
That's the claim, moving AI safety from qualitative guidelines to quantitative metrics. The potential market for things like AI insurance, based on this, they estimate it in the trillions, $2.7 trillion, I think the patent mentioned.
Okay, my head is spinning slightly, but the obvious question comes back. If this is so revolutionary, why couldn't vector databases just evolve into this? Couldn't they just tweak their algorithms, add some features? It feels like they're playing in the same park.
That's a fair question, but the patent argues quite strongly, I think, that it's fundamentally impossible. It's not an incremental step. Look at FIGAT10 again. First, it's an architectural impossibility. Vector databases rely on similarity computation because their addresses are arbitrary. That vector 0.2, 0.7, 0.3 means nothing on its own. You have to compare it. This system, the address 0 by 17, AB0B0C0 is health.cardiac.heartrate. There's no comparison needed. It's baked in. Vector databases can't just switch that off. It's their core mechanic.
Okay, different architecture.
Second, it's a mathematical necessity. Vector spaces define meaning through relative position and distance between points. This system uses an absolute coordinate system where the point itself encodes the meaning. Fundamentally different mathematical concepts.
Relative versus absolute, got it.
Third, remember the card catalog. Vector databases might organize the library better, make the catalog faster, but you still need it. This system, it claims card catalog obsolescence. The catalog layer is gone entirely.
You don't optimize the lookup, you eliminate it.
Precisely. And finally, those emergent properties, The multiplicative scaling, the anti-fragility, the computational morality, they arise from the non-obvious combination of unity and active orthogonality. You can't get those just by improving vector search or just by having addresses equal meaning in a non-orthogonal system. It's the specific synergy of both principles together that unlocks these capabilities. Vector databases, by their very nature of embedding, actually create correlations to find similarity. They can't actively maintain orthogonality in the same way. So yeah, it's a bold claim. It's saying we violated 50 years of established wisdom, we unified position and meaning while enforcing orthogonality, and look what happened. It suggests capabilities that might genuinely exceed what we thought was theoretically possible.
Okay, so wrapping this up, this isn't just, a faster database. It's not just an incremental improvement.
Not at all.
It's proposing a completely different way for information systems to function. A way that could amplify what we intend, be inherently trustworthy, maybe even have a built-in preference for beneficial use.
That seems to be the core message.
So here's something to think about. Imagine a future where your intention translates almost directly into computational action, where trust in complex systems, in AI, isn't just a leap of faith, but something you can actually see, measure, verify at the hardware level. How does that change things? Medical diagnoses, financial markets, scientific discovery, the very way we interact with AI. What stands out most to you when you consider a world where the map literally is the territory?